So in this lecture, we're going to talk more specifically about block designs. So we introduced the concept of a block in the lecture on principles of experimental design. Here, let me just review that concept. A block is just a group of experimental units. The experimental units are the finest division of the experimental material to which different treatments could, in principle, be applied. So since a block is a group of experimental units, we can think of the blocks as a coarser partition of the experimental material than the unit partition. So here on the left is an example for our field, for our agricultural experiment. Because the tractor drives in rows, we define these rows, or I guess these are columns in this case, the columns as the units. So we could apply a different fertilizer treatment to this column than to this column. We could define blocks as just a group of units. So for example, block A would be these two units. Block B could be these two units, C these two, and block D these two. In our rat example, the units were the female rats because each individual female rat could receive either placebo or a hormone treatment. So here is a drawing of what the female rats might look like according to their weight. So here we have 8 female rats, and I've just plotted each female rat as a function of their weight. So this is rat 1 is the lightest weight rat, and rat 6 is the heaviest. The block is just a group of experimental units. So we could define a block as the first block as 1 and 8, the second block as 3 and 5, the third block as 7 and 4, and the fourth block as 2 and 6. Okay, so I've just picked blocks here, but in general, the way you want to pick blocks is you usually pick blocks according to what variables you expect to affect the response. So in this agricultural example, supposing that we expected the yields to vary substantially along the columns, we want to pick blocks that are in similar spatial orientation with respect to the different columns. In the rat example, if we expect the weight of the rat pups to depend on the weight of the mother, then we're picking blocks according to groupings of female rats that have similar weights. So these are both lightweight rats, and these are heavy ones. The reason for this is the purpose of defining blocks is you want to come up with experimental designs, which is the allocation of treatments to units that are balanced with respect to the blocks. So we'll go in more detail about what that means to be balanced. But the main idea here is why you would want to do this is if you have designs that are balanced or close to balance, they produce data sets that allow us to estimate treatment effects accurately. So remember, the goal of an experimental design is to give ourselves the best chance of answering our question, the question of interest in the study. And that usually corresponds to producing data sets that allow us to estimate treatment effects accurately, or in other words, have small variance. So good design can lead to good data, can lead to accurate estimates, which is our real goal. This concept of balance that we'll define in a minute here is often aligned with our goal of accurate estimates, but sometimes there can be subtleties. So we'll go through a couple of those subtleties in the course of this lecture. Okay, so let's talk about our first specific block design, and that's the complete block design. So in the complete block design, we have a treatment factor that has J levels, capital J levels. to generate the complete block design, we create blocks that have J units in each block. And then we assign each treatment exactly once within each block. And this is possible because there are J treatment levels and each block has J units. So here's a picture of a field trial. So the blocks are defined according to the columns. And in this particular experiment, we can divide each column up into 4 squares. And we can assign a different treatment to each square. But any locations within the same square have to get the same treatment. So in that sense, the units are the individual squares. So in this case, there are 16 of those. Each block, which is a collection of 4 squares, has 4 units. And that number of units within each block exactly matches the number of treatments we have, which are varieties of wheat labeled A, B, C, and D. So to generate the complete block design, we just assign each treatment exactly once within each block. So if you look at any one of these columns, A appears exactly once, B appears exactly once, and C appears exactly once, and D appears exactly once. So in order for the complete block design to work is the total number of units has to be a multiple of the number of treatment levels. Here there are 16 units and there are 4 treatment levels. So 16 is a multiple of 4. And you have to define the blocks so that each block has 4 units. And that's exactly what we did here. Now the more commonly used term is the randomized complete block design. All that means is that it's a block design, a complete block design, but you allocate the treatments randomly within each block. So you could put A, B, C, and D in a piece of paper in a hat and then draw out those pieces of paper to assign the treatments to the units within each block. So that would be a way to randomize the assignments. Now, the complete block design is a balanced design. So the definition we're going to use for a balanced design is the following. Each treatment appears an equal number of times in total in the experiment, and each pair of treatments appears together in the same block an equal number of times. So let's verify, this is the design. Let's verify that the complete block design is balanced in this case. So first thing we need to do is count the number of times that each treatment occurs, A, B, C, and D. So A, it appears once, twice, 3 times, 4 times. B is 1, 2, 3, 4. C, 1, 2, 3, 4. D is 1, 2, 3, 4. So each treatment appears 4 times. The other thing we need to satisfy is that each pair of treatments appears together in the same block an equal number of times. So the way you count this is you take each pair. So this, for example, is the pair of treatments A and B. You count the number of times that A and B appear together in the same block. So they appear together here in block 1, here in block 2, here in block 3, and here in block 4. So they appear together in each of the 4 blocks, so you get a 4 here. You can verify for any pair of treatments, they will appear together in the same block 4 times. And that's because it's a complete block design. Every treatment appears exactly once within each block, and so every pair of treatments is together within each of the 4 blocks. Okay, so in balanced designs, the basic idea is that because each treatment appears an equal number of times, no treatment is privileged over any other treatment. And because each pair of treatments appears together in the same block an equal number of times, no treatment comparison is privileged over any other. So let's go back and look again and reiterate what we mean by that. So if you wanted to know whether wheat variety B was better than wheat variety A, one thing you might do is compare the yields from this subplot to this subplot. That would tell you how much better B is doing than A. Likewise, you could, there's lots of comparisons you can make. You can compare this B to this A. And now this is kind of, if you pick these blocks so that because you expect the yields to vary along this horizontal direction, then this comparison of the A in block 3 to the B in block 2 is a less valuable comparison than the comparison between A in block 1 and B in block 1. The reason is that if A in block 3 is different from B in block 2, that difference could be due to the fact that they're in different rows or columns of the field. However, if A in block 1 is different from B in block 1, then you can be more certain that the difference is due to the treatment, the variety of wheat. So if you want to get estimates of comparisons between treatments, it's useful to have the pair of treatments appear together in the same block. So that's the reason that, and because balanced design, each pair of treatments appears together in the same block an equal number of times. That's why we say in balanced design, no treatment comparison is privileged over any other treatment comparison. Now, it's not always going to be possible in every situation to come up with a nice randomized complete block design. So I'm going to talk about some other situations where you have constraints on the blocking structure, where you would use some other sort of design and how to think through the issues there. Okay, so first thing I want to talk about is the incomplete block design. And like I just said, sometimes it's not possible to have exactly J units in each block, or sometimes it just might not make sense to have exactly J units in each block. So let's look at an example here. We're looking at a group of 12 subjects, and this is a memory experiment. And the idea here is there are 4 memory strategies. And you want to see how the different memory strategies that people use improve or help their memory. So you recruit 12 subjects, and you recruit 3 people in their 20s, 3 in their 30s, 3 in their 40s, and 3 in their 50s. So that's their 12 subjects. You think that age may also have an impact on memory. So you want to create blocks according to age. And so the way you pick your blocks is you place the 3 subjects in their 20s in the first block, the 3 subjects in their 30s in the second block, 40s in the third block, 50s in the fourth block. And now here the units are individual people because you can assign exactly one memory strategy to each person. So because you're dividing them up by decade of age, you only have 3 units in each block, whereas you have 4 memory strategies A, B, C, and D. So what do you do in this situation? You can't do a complete block design because you have fewer units in each block than you have treatments. You have 3 units in each block, but 4 treatments. But you can do something called an incomplete block design. So in an incomplete block design, that just means that within each block, you give a subset of the treatments. So in this first block, you give treatments A, B, and C. The second block, treatments D, A, and B. The third block has treatments C, D, and A. And the fourth block has treatments B, C, and D. This design is an example of a balanced incomplete block design. So it's an incomplete block design because you have not all the treatments appear within each block, but it is a balanced design. And let's talk about why that's true. So we said in a balanced design, each treatment appears the same number of times, and each treatment pair appears together in the same block an equal number of times. So let's just do the counting here. So each treatment appears 3 times. So A, 1, 2, 3. B is 1, 2, 3. C is 1, 2, 3. D is 1, 2, 3. And each pair of treatment appears together 2 times. So we won't go through all 6 pairs, but let's just look at A and B. A and B appear together in block 1. They appear together in the second block, but they don't appear together in the third block. It has A but not B. And they don't appear together in the fourth block. It has B but not A. If you pick any other pair, so let's do B and D, they don't appear together in this block. They do in this block, so that's 1. They don't in this block, but they do in this block. So B and D appear together in 2 of the 4 blocks. And if you pick any other pair, you'll find that any pair appears together 2 times. So in this design, each treatment appears the same number of times, and each pair of treatments appears together in the same block the same number of times. So this is a balanced design, and we call this design a balanced incomplete block design. Okay, now this is a situation up here where you can generate a balanced design even though the blocking structure is incomplete. But that's not always possible. So let's just imagine the same experiment, but you had only recruited 2 subjects within each age group. It is possible to have each treatment appear the same number of times. So here there are 8 units, and each treatment appears twice. But it's not possible to have each pair of treatments appear together in the same block an equal number of times. So let's just look at an example. A and B appear together in the first block, but nowhere else. But let's look at A and D. A and D don't appear together ever in the same block. So if we're thinking about how well we'll be able to make comparisons with treatment A, we should be better able to make a comparison between treatments A and B, and less able or have a higher variance on the estimate of the treatment comparison between A and D, because A and D never appear together in the same block. Okay, just like we can have incomplete block designs, we can have something called an overcomplete block design. That means just the opposite, that within each block you have more units than you have treatments. So in the same psychology experiment, suppose you were able to get 5 subjects in each age group. You still have 4 memory strategy that you're interested in, but now you can have, within each block, you can give one of the treatments twice. So in this first block, you did A, B, C, D, and then you did A again. Second block, you did B again. Third block, you do C again. And the fourth block, you do D again. So in this case, this is a balanced design. Each treatment appears an equal number of times. Each treatment appears 5 times if you just go through and count them all up. Now, to talk about how many times each pair of treatments appears together in the same block, now this gets a little bit tricky. So let's think about this. So let's say B and C. B and C appear together in this block, and it appears together, so this would be a 1. Let's see, B and C appear together in this block. But this isn't quite the same scenario here as it is here, because in this block, B appears twice and C appears once. So this block actually gives you more information about the comparison between B and C than this block does. Okay, so what I mean by that is it's not clear how you should count the number of times each pair of treatments appears together in the same block. So for B and C, you should count this as 1, obviously. But for this comparison, do you count this as 2 comparisons or 1 comparison or 1.5 comparison? It's not exactly clear. So that's why I say that this definition of balanced is good for most purposes. Here, balance means each treatment appears an equal number of times and each pair of treatments appears together in the same block an equal number of times. So this is a satisfactory definition for most purposes, but there are some more complicated situations where this definition isn't quite satisfactory. But it will get us pretty far, and I think we can sort of just kind of intuitively realize that this is a balanced design. One way of thinking about it is if you just restrict to looking at the first 4 units in each group, this is a complete block design. And then basically you take each treatment and append it to one of the 4 blocks. All right, so just to reiterate, the goal for experimental design is to give yourself the best chance of answering your question of interest. Oftentimes, the balanced design is the right design for achieving that goal, but balance itself is not the goal. The goal is to answer the question, which often means the same thing as reducing the variance of our estimates of the treatment effects. So the goal is to answer the question, not necessarily balance. Let's just look at a couple of examples that are a little bit more subtle to that. A little bit more subtle than that. So sometimes we might compare about certain treatment comparisons more than others. So in this example, you have 4 treatments, A, B, C, and D. You have a situation where you have 4 blocks, and each of the blocks has 4 units, so you could do a complete block design. But in this specific example, B is like an experimental version of A, and D is an experimental version of C. So A is a well-established treatment, C is a well-established treatment, but B and D are kind of experimental versions of that. So because you have 4 treatments, 4 blocks, 4 units each, you could do a complete block design. But if you really cared more about this comparison between A and B and the comparison between C and D, then you might prefer to do a design like this, where A and B appear together twice in this block and twice in this block, but you never see, for example, A and D together in the same block. So this particular design would give more information about comparisons between A and B and C and D, and less information about comparison between A and D, for example. Another situation is where the appropriate blocking structure might not lend itself to a balanced design. So here's one example. You have 3 treatments, A, B, and C. The first block has 3 units, the second block has 3 units, and the third block has 4 units. So in a diagram, you can think of it like this, where these are the units in block 1, these are the units in block 2, and these are the units in block 3. If you wanted to preserve balance, you could just ignore that extra block, that extra unit in block 3, and then have a balanced design here. But this is really not as good as just doing a balanced design in this part of the blocking structure, and then just doing an extra run of A here. This will be a sort of a uniformly better design because it has more data than this one. So the general principle here is don't sacrifice data that can help you answer your question just in order to achieve a balanced design. All right, so the next thing I want to talk about are a more formal way to evaluate the designs. And that formal way of evaluating the designs is to look at the variance of the treatment effects under certain models and certain designs. All right, so we'll need some notation here. Little y ijk is the ith observation from block J and treatment K. So you may have multiple observations from the same treatment level in the same block, which is why you need this extra index I to distinguish those multiples. An additive model would look like this. So you have block effects, these are the BJs, and you have treatment effects, these are the CKs plus random error. What you're interested in this experiment is estimating the variance of the treatment effects. And here we'll just have two treatment levels, 1 and 2. And so what we'd like to estimate is C2 minus C1. That would be the effect of the treatment. And so in order to estimate that well, you want the variance of the estimator to be small. So let's put this in the context of our rat experiment. We have 20 female rats and 10 males. We're going to block the female rats into groups of 2. And we're going to have the same male rat for each group of 2 females. So each of the letters here corresponds to a female rat. The number at the top corresponds to which male rat will impregnate the female rat. And then the specific letter that gets used is the treatment that you're going to apply. So T is for the treatment, C is for control. So here, J, capital J is 10, the number of blocks. Those correspond to the 10 male rats. And capital K is 2, that's the number of treatments, control group versus treatment group. So you can just calculate. I won't go through the calculations of how you actually get this. But in R, you can calculate what is the variance of this least squares estimate of the treatment effect. And for this design, it ends up being sigma squared times 0.2. Now, in general, it looks like I've not randomized treatment versus control. In general, you'd want to flip a coin, but actually the randomization doesn't affect the calculation of the variance of the treatment effect. Okay, now let's think about, so this is a balanced design. This actually is a complete block design because each block has 2 units, and within each block you assign each of the treatment levels exactly once. This design is design 2, is a balanced design, but it's not a complete block design. You'll notice that the thing I changed from design 1 to design 2 is for male rat 9, we gave the treatment to both of the female rats, and for male rat 10, we gave the control or the placebo to both of the female rats. So these two designs differ just in what treatments were assigned to the female rats that were paired with male rats 9 and 10. If you go through the same exercise and calculate what's the variance of this estimator for the treatment effect, it's sigma squared times 0.25. And so this design has a larger variance for the estimator for the treatment effect than this design. So we prefer this design to this design. Even though this design has a balance to it, this part of the design is balanced, and so is this part of the design. So we can think of this as a balanced design, but it's not optimal. So it's a balanced design that's not optimal. Design 1 is the design that's actually optimal. It has the smallest variance of the estimator of the treatment effect. All right, the last thing I want to talk about in this lecture are situations when you have multiple blocking factors. This actually comes up a lot. I think the simplest way to start talking about this is with our agricultural example. So in the previous examples, we treated the columns as the blocks. The reason for that is because we imagined that the yields would vary substantially in the east-west direction. So we want to group units that have similar values of longitude, and then make things balanced with respect to longitude. But in reality, you may expect the yield to vary both in the east-west direction and the north-south direction. So you'd want to have a design that's balanced with respect to both of these directions. So you could have two blocking partitions. So you can have a column blocking partition and a row blocking partition. And the idea here is you'd want to come up with a design that's balanced with respect to both of the blocking partitions. So let's think about the left one versus the right one. The left one is balanced with respect to the columns. So if you look at each column, each treatment appears exactly once. But if you look at the rows, that's not true. So in the second row, B appears twice. And in the fourth row, C appears twice. So this is a design that's balanced with respect to columns, but it's not balanced with respect to rows. On the other hand, this design is balanced with respect to both rows and columns. So if you wanted balance with respect to both of these, you would prefer this design. This design has a special name. It's called a Latin square. So a Latin square is just a complete block design in both of these sets of blocks. And if you think about this carefully, you really need a special blocking structure in order for you to achieve a Latin square. So what you need to happen is if you have J treatment levels, it has to be a square. So you have to have J squared units. In this case, the units are the subplots of the field. And then you need two sets of blocks, and each of those two sets of blocks, you need to have J of them, and each of these J blocks has to have J units. So that's exactly satisfied here. The first set of blocks are the columns. There are 4 of those. That's capital J, the number of treatments. And each of those blocks has 4 units. And the same is true of the rows. So there are J equals 4 blocks of rows. And each of those blocks has 4 or J units. So you have to have a very special structure. It has to be a square like this. And the number of rows and columns in the square has to be equal to the number of treatments. So you can't always apply the Latin square, but in situations like this you can. Okay, that's it for block designs. Of course, things can get much more complicated. The next thing we'll talk about is what to do when you have more than 2 blocking factors. As you can imagine, you have to be very careful about that.